Picture this. A massive ship, weighing as much as 80,000 tons, floating effortlessly on water. It seems to defy logic, doesn't it? The Queen Mary 2, a behemoth of the seas, stays afloat despite its enormous weight. But how? The answer lies in a principle discovered over 2,000 years ago, and it's revolutionized shipbuilding ever since. The question that begs to be answered is, how can something so colossal remain buoyant? What ancient wisdom allows these giants of the ocean to defy gravity and sail across vast expanses of water? The secret lies in a concept so fundamental yet so ingenious that it has shaped maritime engineering for millennia. Understanding this principle isn't just a matter of satisfying our curiosity, it's crucial for the safety of every vessel that takes to the seas, from the smallest fishing boat to the mightiest aircraft carrier. As we unravel this mystery, we'll see how this ancient knowledge continues to guide modern shipbuilding, ensuring the security of countless lives and cargo on the high seas. As we explore the science behind maritime safety, we encounter a paradox. How can water, a substance we can easily push aside with our hands, support the weight of colossal ships? The answer involves a delicate balance between two opposing forces, and understanding it is crucial for every vessel that ventures into the open ocean. Imagine filling a bathtub and placing a small toy boat on the surface. As the boat settles, you might notice a subtle change in the water level. This simple observation holds the key to understanding how massive ships stay afloat. The principle at work here is water displacement, and it's the foundation of maritime engineering. When an object enters water, it pushes aside or displaces a volume of water equal to its own weight. This displaced water creates an upward force known as buoyancy. For a ship to float, it must displace its own weight in water. It's a delicate balance that allows even the largest vessels to traverse the seas safely. Let's consider the scale of this phenomenon. A ship weighing 80,000 tons must displace 80,000 tons of water to remain buoyant. It's a staggering amount, equivalent to the weight of about 13,000 adult African elephants. Yet, this is precisely what happens when a large cruise ship or cargo vessel sets sail. As a ship is loaded with cargo, it sits lower in the water. This isn't a sign of impending danger, but rather a demonstration of the principle in action. The ship displaces more water until the buoyant force matches its new weight. This process illustrates how ships can carry heavy loads without sinking, a feat that seems to defy logic at first glance. The relationship between weight and water displacement is fundamental to naval architecture. Engineers design ship hulls to ensure they can displace enough water to support the vessel's weight, even when fully loaded. It's a delicate balance that requires precise calculations and an understanding of various factors, including the density of different water bodies. This principle extends beyond just keeping ships afloat. It's also crucial for determining how deep a ship can safely sit in the water. Enter the plimsoll line, a vital safety feature on ships. This marking on a ship's hull indicates the maximum depth to which it can safely sit in water based on its weight and the water's density. It's a visual representation of the balance between the ship's weight and its buoyant capacity, ensuring that vessels don't exceed their safe limits. Understanding water displacement isn't just about keeping ships afloat. It's about optimizing their performance and ensuring safety at sea. By manipulating the shape and size of a ship's hull, naval architects can influence how it interacts with water, affecting everything from stability to fuel efficiency. The principle of water displacement applies equally to a small fishing boat and a massive oil tanker. The difference lies in scale. A fishing boat might displace a few tons of water while a supertanker could displace hundreds of thousands of tons. Yet the underlying physics remains the same, showcasing the universal nature of this maritime principle. The physics governing massive ships today was unraveled by an ancient Greek mathematician in his bathtub. How did a simple act of personal hygiene lead to a principle that would shape maritime engineering for centuries to come? This is the story of Archimedes and his famous Eureka Moment, a discovery that illuminated the mysteries of buoyancy and laid the foundation for modern naval architecture. Imagine yourself in ancient Syracuse, a Greek city-state on the island of Sicily. The year is around 250 BCE and the streets are buzzing with the usual activity of a thriving Mediterranean port. Suddenly, the peace is shattered by the sight of a naked man running through the streets shouting Eureka at the top of his lungs. This man was none other than Archimedes, one of the greatest mathematicians and inventors of all time. What could have caused such an unusual spectacle? The story goes that Archimedes had been tasked by the king to determine whether a crown was made of pure gold, or if the goldsmith had fraudulently mixed in some silver. Pondering this problem, Archimedes stepped into his bath and noticed that the water level rose as he submerged himself. In that moment he realized that the volume of water displaced was equal to the volume of his body. This observation led Archimedes to formulate his famous principle: any object, wholly or partially immersed in a fluid, is buoyed up by a force equal to the weight of the fluid displaced by the object. In simpler terms, if an object weighs less than the water it displaces, it will float. If it weighs more, it will sink. The implications of this principle are far-reaching, especially in the realm of shipbuilding. Consider our earlier example of the Queen Mary II. This massive vessel, weighing 80,000 tons, stays afloat because it displaces more than 80,000 tons of water. The ship's hull is designed to displace a volume of water whose weight equals that of the ship and its contents. But Archimedes' principle isn't just about large ships. It applies to all objects, regardless of their size or density. A small wooden toy boat floats using the same principle as a massive oil tanker. The key difference lies in the volume of water displaced relative to the object's weight. This universal application of Archimedes' principle is what makes it so powerful in naval engineering. Whether designing a small fishing boat or a colossal container ship, engineers must ensure that the vessel displaces enough water to create a buoyant force equal to its total weight. This calculation includes not just the ship's structure, but also its cargo, fuel, and even the weight of the crew and passengers. The beauty of Archimedes' discovery lies in its simplicity and its ability to explain complex phenomena. It allows us to understand why a steel ship can float while a small pebble sinks. The ship, despite being made of a material denser than water, is shaped to displace a large volume of water relative to its weight. The pebble, on the other hand, displaces only a small amount of water compared to its weight. Archimedes' principle also explains why ships sit lower in the water as they are loaded with cargo. As the weight increases, the ship must displace more water to maintain buoyancy. This is why ships have a maximum load capacity. There's a limit to how much water they can displace before they become unstable or begin to sink. The impact of Archimedes' bathtub revelation extends far beyond the realm of ships. It forms the basis for understanding the behavior of submarines, hot air balloons, and even the buoyancy of fish in the ocean. It's a testament to the power of observation and the enduring nature of fundamental scientific principles. Archimedes' insight revolutionized our understanding of buoyancy, but it's only part of the story. What invisible force allows modern ships to carry unimaginable weights across vast oceans? The answer lies in a delicate balance between substance and emptiness, carefully calculated by today's naval engineers. When you think of a ship, you might imagine a solid, hulking mass of steel. But what if I told you that ships are designed to be mostly empty? This counterintuitive approach is the key to keeping massive vessels afloat, and it's a testament to the ingenuity of modern naval architecture. The hull of a ship is its most critical component when it comes to buoyancy. Naval architects design hulls to maximize water displacement, allowing ships to float even when carrying enormous loads. The shape of the hull determines how much water the ship can push aside, directly affecting its buoyancy. By creating hulls with broad, flat bottoms and gradually sloping sides, engineers ensure that ships displace the maximum amount of water possible. But the real magic happens inside the hull. Contrary to what you might expect, much of a ship's interior is filled with air. These air-filled spaces serve a crucial purpose. They significantly reduce the ship's overall density. Remember, for an object to float, it must be less dense than the water it displaces. By incorporating large air pockets into the design, naval architects effectively create a vessel that, on average, is less dense than water. These air-filled compartments aren't just empty voids. They're carefully designed and positioned to optimize the ship's performance and safety. Some serve as ballast tanks, which can be filled with water or emptied to adjust the ship's buoyancy and stability. Others house essential equipment or serve as storage areas. The key is striking the right balance between functional space and buoyancy-enhancing emptiness. As ships are loaded with cargo, fuel, and passengers, they naturally sit lower in the water. This is where another crucial element of ship design comes into play: the plimsoll line. Named after Samuel Plimsoll, a British politician who championed maritime safety in the 19th century, This marking on a ship's hull indicates the maximum safe loading level under various conditions. The plimsoll line isn't just a simple horizontal line. It's a complex set of markings that account for different water densities and temperatures. For instance, a ship can safely sit lower in salt water than in fresh water due to the difference in density. The plimsoll line ensures that no matter where a ship is sailing or what it's carrying, it always displaces enough water to remain buoyant and stable. Naval architects use sophisticated computer models and calculations to determine the optimal hull shape, internal layout, and loading capacity for each ship they design. They must consider not only the principles of buoyancy, but also factors like stability, fuel efficiency, and seaworthiness. It's a complex balancing act that requires both scientific precision and creative problem solving. The result of this careful design process is nothing short of remarkable. Modern cargo ships can carry tens of thousands of containers across vast oceans. Cruise ships the size of small cities glide effortlessly through the waves. Oil tankers transport millions of barrels of crude oil without sinking under the immense weight. All of this is possible because of the clever manipulation of buoyancy principles first discovered by Archimedes over 2 millennia ago. However, there's more to keeping these colossal vessels afloat than just buoyancy. What if I told you that the key to a ship's survival lies in its ability to dance with the waves? The science behind this maritime ballet is both fascinating and crucial. Imagine standing on the deck of a massive cruise ship, feeling the gentle sway of the ocean beneath your feet. Now picture that same ship facing towering waves in a storm. How does it remain upright and stable? The answer lies in a combination of clever design features and cutting-edge technology that work together to keep these floating cities balanced, even in the roughest seas. At the heart of a ship's stability is its center of gravity. Naval architects carefully calculate and control this point, ensuring it's low enough to prevent the ship from toppling over. They achieve this by distributing weight strategically throughout the vessel. Heavy equipment and cargo are placed low in the hull, while lighter structures occupy the upper decks. This weight distribution creates a natural resistance to rolling, much like a balanced scale. But weight distribution alone isn't enough to combat the relentless forces of the ocean. That's where the shape of the hull comes into play. Modern ships often feature a U-shaped hull design, which offers several advantages in terms of stability. The rounded bottom of the ship may cause it to move through the water more slowly, but it also limits rocking and motion. As one expert puts it, this is a good thing, as anyone prone to seasickness will tell you. The U-shaped hull works in tandem with another crucial feature, the ship's beam or width. A wider ship is generally more stable, as it requires more force to tilt it to one side. However, naval architects must strike a delicate balance between stability and other factors like speed and fuel efficiency. It's a complex dance of trade-offs that requires extensive calculations and modeling. Even with these passive stability features, large ships often need an extra boost to stay level in rough seas. Enter the stabilizers. Think of them as the ship's balance beam. Active stabilizers, such as fins that extend underwater, can adjust to the waves in real time, providing immediate stabilization. These fins work by generating opposing forces to counteract the ship's roll, much like how you might extend your arms to regain balance on a tightrope. For situations where active stabilizers aren't enough, ships employ additional methods to maintain equilibrium. Anti-roll tanks, for example, contain fluid that can be moved from one side of the ship to the other, adjusting the weight distribution as needed. It's like having a giant water balloon inside the ship that can be squeezed to counteract the forces of the waves. But what about those extreme conditions, when the sea seems determined to test a ship's limits? That's where the concept of metacentric height comes into play. This technical term refers to a ship's ability to right itself after being tilted. A higher metacentric height means greater stability, but it can also lead to a more uncomfortable ride for passengers. Naval architects must find the sweet spot that ensures safety without sacrificing comfort. The average density of a ship, including all the air inside, must remain less than that of the water it displaces to ensure buoyancy. This balance is critical for preventing capsizing and maintaining stability in turbulent waters. It's a constant juggling act, with the ship's systems working tirelessly to maintain equilibrium as conditions change. In the most extreme cases, ships may encounter rogue waves, massive walls of water that tower above the surrounding sea. These rare but dangerous phenomena can pose a significant threat to even the most well-designed vessels. To combat this risk, Modern ships are built with reinforced hulls and advanced weather routing systems that help captains avoid potentially hazardous areas. The ocean, for all its beauty, can be a merciless adversary. Despite our technological advancements and engineering prowess, nature sometimes reminds us of its raw, unbridled power. Imagine a ship longer than 3 football fields suddenly facing a wave that could swallow it whole. What happens in those crucial moments when maritime engineering meets its match? Enter the realm of rogue waves, a phenomenon that has long been the stuff of maritime legend. These massive walls of water, also known as freak waves, can tower over surrounding waves, posing a serious threat to even the largest vessels. But what exactly are rogue waves, and why are they so dangerous? Rogue waves are defined as surface waves that exceed twice the significant wave height of the surrounding sea. In simpler terms, they're abnormally large waves that seem to appear out of nowhere. The Draupner wave, recorded in 1995, was the first confirmed measurement of a rogue wave. Standing at a staggering 26 meters high, it challenged previous scientific models and forced us to reconsider our understanding of ocean dynamics. The destructive force of these waves is almost beyond comprehension. They can exert pressures of up to 500 metric tons per square meter on a ship's hull. To put that into perspective, it's like having the weight of 100 elephants pressing against every square meter of the ship's surface. This immense force can easily exceed the structural limits of modern ships, leading to catastrophic failures. When ships encounter rogue waves, they face risks that go beyond the realm of normal maritime hazards. The sheer size and force of these waves can cause ships to capsize or suffer severe structural damage. The MS München, a German lash carrier, is believed to have sunk due to a rogue wave in 1978. This incident highlighted the potential danger these waves pose to large vessels and sparked increased research into the phenomenon. What makes rogue waves particularly treacherous is their unpredictability. Unlike tsunamis, which are caused by seismic events and involve the entire water column, rogue waves arise from typical ocean waves through a process called constructive interference. This occurs when waves traveling at different speeds or directions combine, creating a massive surge of water. The sudden and unexpected nature of these waves leaves little time for ships to prepare or take evasive action. The RMS Queen Mary, a ship known for its size and grandeur, nearly capsized after encountering a 28-meter rogue wave in 1943. This incident serves as a stark reminder that even the largest and most well-designed ships are not immune to the ocean's fury. It's estimated that a significant number of vessel losses throughout history may be attributable to these monstrous waves. So, how do modern ships defend against such an unpredictable threat? Naval architects and engineers have developed various strategies to enhance ship survivability in extreme conditions. One approach involves strengthening the ship's hull and superstructure to withstand higher pressures. Advanced materials and construction techniques are employed to create more resilient vessels capable of absorbing the enormous forces exerted by rogue waves. Another critical aspect of defense against rogue waves is improved weather forecasting and route planning. While predicting individual rogue waves remains challenging, meteorologists can identify areas with conditions favorable for their formation. Ship captains use this information to plot safer courses, avoiding regions where rogue waves are more likely to occur. Modern ships are also equipped with sophisticated sensors and monitoring systems that can detect changes in wave patterns and sea conditions. These early warning systems provide crucial seconds for the crew to prepare for potential impacts, securing loose items and adjusting the ship's heading to better withstand the oncoming wave. Despite these advancements, the battle against rogue waves is far from over. The phenomenon continues to challenge our understanding of ocean dynamics and push the limits of maritime engineering. As we gather more data and refine our models, we hope to develop even more effective strategies for predicting and surviving these monstrous waves. As we reflect on the marvels of maritime engineering, we're struck by the enduring power of ancient wisdom. The principles discovered by Archimedes over 2 millennia ago continue to shape our understanding of buoyancy and guide the design of modern vessels. From the humble fishing boat to the mightiest ocean liner, every ship that sails the seas owes its buoyancy to these fundamental laws of physics. The next time you see a massive ship gliding effortlessly across the water, take a moment to appreciate the intricate balance of forces at play. It's a testament to human ingenuity, and our ability to harness the laws of nature. The plimsoll line on a ship's hull stands as a visible reminder of this delicate equilibrium, marking the fine line between floating and sinking. As we continue to push the boundaries of naval architecture, one can't help but wonder, what other seemingly impossible feats might science explain in the future?